Right. So welcome everyone. So it's our pleasure to have today with us Debadeepta Dey and Shital Shah. So they're both, working in Microsoft research at Redmond, USA, and Debadeepta is researching the reinforcement learning group, and Shital is also a principal research engineer in the reinforcement learning group. And today they'll be speaking about their project named Ranking Architectures by their feature extraction capabilities, and also they'll make a short intro of their ArcAI NAS library, which they both co-authored. So without further ado, so the floor is all yours.
Thanks a lot, Arbor. Thanks a lot, first of all, for having us here. We are very excited. And we love this seminar series. And when we, especially sometimes, even if time zone doesn't allow, I try to at least go on YouTube and watch the recordings that we have been doing since April. It helps me keep up with all the great work happening in the area of AutoML. Without further ado, today we are going to talk about how to rank architectures by their feature extraction capabilities. So let's see if, okay, it doesn't want to move. Okay, but it still move on that. Okay. Okay, so if you think about discrete NAS methods, right? Like, and I'm going to assume that the audience here has some familiarity with neural architecture search methods. And in most discrete NAS methods, where methods can mostly be like weight sharing, one-shot methods, or without weight sharing, discrete NAS methods. Examples include like local search, Bayesian optimization, model-free RL, which was one of the earlier papers in 2016, and contextual bandits. You can do all kinds of cool discrete search algorithms. The big bottleneck is evaluating architectures, right? Like almost all these architecture algorithms, discrete NAS algorithms, can be represented as, oh, there's a search space, we have some control or update law from which we will sample architectures. Let me make sure I have my pointer on. Yeah, we will sample architectures, we will evaluate them and get some training or validation error and go and update our controller and ask like, what is the next set of our architectures to sample, right? And this is how at a high level, all discrete NAS algorithms look like, search algorithms look like, right? Especially in search spaces, which are massive, like the Natsbench 301 search space, which has easily 10 to the power 18 architectures or more. Right, and then the whole hope is that your controller has an update law which is efficient and efficiently explores. And all of the time, as you can imagine, goes here because in NAS you have to function evaluation is expensive, and you have to come up with a method to evaluate these architectures as quickly as possible, but without fully training them. Because let's say you are doing on ImageNet or Wikitext 103 language modeling, your evaluation for each architecture that you sample, if you do full training, can easily take like, 1 day. And that's one architecture, right? Like on, let's say, an 8 GPU machine with distributed V100 GPUs. And this is very, very expensive. And so most people have come up with many different ways in order to cut down this evaluation time, such that your final ranking, your let's say your Spearman rank correlation or your Kendall tau with respect to the final ranking that you ground truth ranking is respected as much as possible, but allows you to touch each architecture as lightly as possible, so that you don't have to spend too much compute on each architecture. And that's really the main goal when it comes to how we should evaluate architectures, maintain ranking with at least with respect to the ground truth if you had fully trained it. So the current approaches is the most organic thing you can do is pick a small number of epochs and hope that this is enough, right? And maybe I'm on ImageNet, maybe I'm going to pick 20, 30, 40. I remember when we were writing Petri dish, we were like, well, let's do 40 epochs. And then Echo, who was the first author running all the experiments, as everything was like, why is 40 epochs enough? Maybe we should do 80. With 80, it was giving me slightly better results. So we were never really sure, what number of epochs to use, because obviously, the more epochs we used, results improved a bit. But then it also seemed that there was a diminishing returns, and the more and more epochs didn't mean linearly increasing number of inaccuracy, final accuracy on the Pareto frontier. So it was not very easy to decide this hyperparameter. And this is quite an important hyperparameter in a search algorithm. And in very recent work, there has been many like training-less measures, like where the whole idea is that we do not even train a network more for even one epoch or even one mini batch. Usually, like people will look at the statistics of one mini batch of data or a few mini batches of data, which costs almost negligible, right? So you can just call them as zero cost measures. And there have been measures which try to lift and shift pruning at initialization methods, as well as like a method proposed by Mellor et al, which looks at the sensitivity of the entire architecture of gradients near the data points to figure out if how correlated are the feature maps, and based if they are not correlated, that's good. If they are correlated, that's bad. And with that kind of intuition of the network being able to discriminate between data points at initialization itself, inspired a little bit by NTK theory, they have been able to propose some promising measures. And we will look deeper into all of these training-less measures as in the later part of the talk. So without further ado, what I will do is I will just give out algorithmically our proposed method, and then we will go into the motivation, right? So just mechanistically, let me just say the method, which I hope will come across as very simple. Also, in any part of the talk, feel free to just interrupt, and we are very happy to make this a discussion and get feedback and anything else that you would want to, which appears confusing. We have a relatively small group, so we can make it a fun discussion. So fear proceeds by first training a fast or shallow learner, right? Like think like, I tie your hands behind your back and say you are handicapped from using deep learning, or at least a very deep network. You can maybe use a linear classifier or a two-layer network, a random forest, random kitchen sink of features, etc. You think of like pre-2012. What would be your go-to method if you are not going to use deep learning? Take that method and train it on your dataset and task loss function of choice of interest, and that will give you a training or validation error threshold, right? Like let's say I take a linear classifier or a random forest on CIFAR 10. And I ask like, what is the best thing that this can do? And it doesn't need to be the best thing that shallow learner can do. It can be just any, like, reasonable method, reasonably powerful method, and it will give you something. And let's say on CIFAR 10, it gives you 60% accuracy. Just as a side note, if you don't do CIFAR 10 training, even a simple ResNet 50 can easily get you above 90%, like, in a few hours of training, right? So 60% is not that impressive today. But this comes, and obviously, like, deep networks are much more powerful, and depending on how many layers you use and what your training procedure is, you can easily get up to like 98, 99%. If you do 1500 epochs and data augmentation enabled with fast augment or some auto augment, you will get close to 99% on CIFAR 10. Okay, so but and this is really fast, right? So this particular stage is like 30 minutes on your laptop on a data set, at least like CIFAR 10. 2 hours on ImageNet you can do on a laptop event, right? So let's say you get 60% as, let's say, a training error that you were able to get. Now in stage 1, you take an architecture from your search space and you train this architecture until you hit this threshold accuracy. Okay, and then the output of stage 1 is this partially trained architecture, which is around that, which you have cut off training at 60%, right? It hit 60% training error or validation error, and you just shut it off. Now what you do in stage 2 is you freeze most of the architecture, and you continue and you just train. So let's say in our particular experiments that we will show, we freeze around 75% of the layers, which roughly amounts to around 55% of the parameters, and we train the last few layers for a few more epochs, usually 5 or 10. And this doesn't take much time. This is like 10 seconds per epoch on CIFAR 10 on a V100, or 15 seconds on a V100. And then you do this for all the architectures you care about, and the way you sample architectures comes from your search method. So in this work, we are agnostic to the particular discrete search method. It can be any discrete search method. And so you get this final, train or validation accuracy of your architecture trained in this particular two-stage manner, right? So there is this first phase of train until threshold accuracy, and then you freeze most of the network. And this allows, and then you take this final score and you rank all your architectures by this final score that you get of training or validation accuracy. I hope the process, and this is the critical part of the talk, but I hope, and then we will go into motivation and why we think this is a good method and what are the pros and cons. But I hope this mechanistically, this process was clear. And if you have any doubts, feel free to ask me now. I'm not unable to monitor chat exactly, so feel free to just speak up if you have any problems. Okay, so I'll take silence to mean that this was clear. So now we will go into okay, what is really going on? Why this weird phenomenon instead of taking choosing a few number of epochs, right? So there has been increasing evidence from more theoretical work which analyze the training of deep networks, gradient-based training of deep networks, is that deep networks train mostly in two stages. That in stage one, what you will call as the NTK regime, the network will use its initialization as a kernel embedding and does kernel regression. Note in NTK, in the original NTK paper, which is analyzed mostly for infinitely wide networks, the features are constant, right? Like when the network is infinitely wide, the features don't change, or the implicit kernel induced by the features don't change. But we are talking about finite width networks, so the features will change, and that's expected and desirable. But the phenomenon still happens where the network uses a kernel which is changing, but it does kernel regression, right? And that's stage one. And then secondly, the network then in the second phase, once this initial feature training has happened, it further trains the features to learn the decision boundary, right? Let's say you are doing classification, you are image classification, you take these features and then learn the classifier using these features. And these features will keep changing a lot too, a bit too in the second stage, but not too much away from the features learned in stage one. And if you think about the process that I just mechanistically outlined, what we hope will happen is that this threshold that comes from this linear, let's say a shallow learner or some powerful, let's say kernel method, if you train a network until the threshold that was accuracy that was achieved by the shallow network, you should have escaped the feature learning first stage regime, right? That if my network, if let's say a kernel method gets 60%, and I train the network until I hit 60% training error, right? Like you have or validation error, you don't have access to the test set. The test set is sacred. You should have escaped the feature learning regime that was induced by a powerful kernel, right? Like in a shallow network. So after that, then when we do the second stage where we freeze most of the architecture and continue training, we are basically turning the architecture into a feature extractor. This is a very common trick. You usually do this if you have worked in semi-supervised learning or unsupervised learning. People do fine tuning this way, right? Like in Vision, you train on ImageNet, fine tune, freeze everything, use it as a feature extractor for any, let's say, downstream task. And you can fine tune maybe only the last few layers, and that itself works pretty well, right? And the hypothesis here is that the performance of your architecture depends upon the power of the features learned in stage one. So if, for example, this is a very bad architecture, the features it will learn in stage one are not going to be that great. So the classifier training, when you train the stage two, is not going to be as powerful, which will be reflected in the final train and validation accuracies. Like, for example, if this was an architecture of mostly all skip connects, you don't expect it that the features it will learn will be good enough to produce good training and validation accuracy. So this is the motivation behind why there is this two-stage training procedure. And it's basically to mimic the two-stage training that theory suggests gradient-based training of neural networks do implicitly. Okay, any questions here? And if not, and then I can move on. Okay, the second thing, motivation, is that lower layers, right? Like, so there has been a series of papers from Maitra Raghu from Google Brain and follow-up papers from Google Brain, which show this really nice phenomenon where they empirically look using, like, canonical correlation analysis and then later on centered kernel analysis into the hidden implicit representation of networks as they train, right? Like, so if you take, for example, ResNet, and I think ConvNet, if I believe, is very VGG-like. What this plot is showing is on the correlation, and correlation in this higher order correlation, like, let's say, canonical correlation analysis. So it's like a nonlinear correlation, not linear, between the distribution of activations of layers at the end of training versus, let's say, during training, right? Like, this could be like midpoint of training. So, well, actually, this is the initialization, this particular plot, and then 35%, 75%, 100% trained. And you will see that early layers, like, let's see, are very highly correlated with the layer activations at the end of training, which means that the early layers train very fast, like even a few epochs of training suffices to train the feature extractor, right? Like, which is usually in the early layers, at least in CNNs. And those early layers don't change much in representation even as training goes on, and only later on, and you can see this two-stage phenomenon happening empirically, that the end layers start to become correlated, train with their with themselves, with their final training at the end of, like, 100% of training in the second part of training, right? Like, but this thing happens blazingly fast and doesn't change much, whereas the second part happens later, of the later layers. And this is like further empirical evidence that of this two-stage training of neural networks. So, and you can, what this particular process fundamentally exposes is also this following phenomenon, and this is empirically validated. And what we did is we took 1,000 architectures, randomly sampled from Natsbench. Natsbench is nothing but the journal version of Natsbench 201, where they have made things like improved the API a bit and added a size search space. But on the original Natsbench 201, which in Natsbench is called the topology search space, we sampled 1,000 architectures, and this shows on the x-axis as the wall clock time, and this is all the experiments are done on V100 machines on the same hardware, so the times at least are self-consistent. That on the wall clock time to reach threshold accuracy, right, is the x-axis, whereas y-axis is the final accuracy, the final test score. And since this isn't part of the benchmark, this is just, we just can look them up from the table, and you can see that architectures which are weak, like architectures which don't go on to have good final performance here, like, this 80, 65 and whatnot, invariably take much longer to train in order to achieve this threshold accuracy of, let's say, 60%. And the reason we have, so it's on CIFAR 10 it's 60%, on CIFAR 100 it's 30%, on ImageNet 16 it's 20%, is because we took a shallow pipeline, and when we ran it on each of these 3 data sets, these are the numbers they could achieve, right? Which are not very impressive from deep learning perspective, but it gives us that shallow kernel performance very quickly. And we see this particular phenomenon as well, is that weak architectures invariably take much longer. There are, okay, but note the converse is not true, that it doesn't mean that there aren't weak architectures that don't train quickly. Like, for example, like here, this is relatively weak. This is pretty relatively weak. Like, there are all these architectures here, relatively weak. which can quickly train. For example, if you take an architecture which is only skip connects, right? There are not a lot of parameters in it. There's not a lot of work for backprop to do. It will train very fast, but and achieve something, but it will not be very good, right? But what the key thing to see is that there are no late bloomers. Like, see this large empty space, that weak architectures don't, like there are no architectures which suddenly become good as training goes on, right? Like, people don't suddenly jump up here. And this area is completely free. And we can use this, when we use fear in order to rank architectures, this is something you can exploit to early terminate architectures. And I will show you how with a simple example from random search. Oh, yeah, and thanks to the hard work of Natsbench 301 authors, yesterday in 25 minutes, I was able to download all the training logs and plot this same phenomenon where x-axis is time to reach 60% accuracy. This is CFAR 10, and y-axis is the final accuracy that it would is the final test accuracy it would reach if you were to do full training on it. And you see the similar phenomenon that vast number of weak architectures take either much longer and obviously they do, or if they train fast, they don't achieve very good final performance. And this space is again relatively empty. You may be wondering, is that, hey, Dey, if this is true, why do I need to do this two-stage phenomenon, which seems relatively complicated? Why can't I just pick a number of epochs and be happy with it? Like, let's say, let me pick 10 epochs, and in 10 epochs, whoever has made the most progress, right? Let's say the strong architectures would have reached higher validation threshold or training threshold, training accuracy, whereas the weak ones would be lagging behind. So I just pick the argmax according to that, and that race should be pretty indicative if this is true. And while that may sound tempting, look at these columns that are here, right? Like, so you need to be able to differentiate between these, right? Like, so if, let's say, if I do 5, 10 epochs or 20 epochs of training, I can't just pick argmax because these people will still be relatively confused between them. You need to at least get beyond feature training and then rank them according to their feature architectures. Okay, one advantage of fear is that you don't need to guess how many epochs of training you need to do per search space task dataset, right? And then because if I a lot of us are quite familiar. If you work in NAS, you have probably beaten to death. You probably know every image in CFAR 10 and 100 and ImageNet and what the statistics are of training any kind of network on them. So you have a lot of domain knowledge. But if I give you like a very wonky new data set, which trust me, in industry and product groups, you will see data sets which look nothing like academic data sets. You may not be sure if what worked on ImageNet or CFAR 100 is going to work, if the same hyperparameters will work here in your search algorithm, right? So what we can do is, and usually shallow methods tend to be not that hyperparameter sensitive. They don't are usually especially if I take a linear classifier with expanded features in order to get some kernel nonlinearities, it's pretty easy. And because it doesn't take much time, I can even do some hyperparameter tuning on that, as opposed to doing hyperparameter tuning on my search algorithm, which is the very expensive procedure, right? Which is not only just training one architecture, but training potentially hundreds of architectures. So at best, instead of guessing epochs per training on your search algorithm, NAS algorithm, you may want to do some hyperparameter tuning, if at all, on your shallow method, which is much cheaper because function evaluation there is much easier. And at least you don't have to guess how many epochs of training you would need, right? Because the difficulty would become implicit, right? As you saw that before, that hey, my shallow method, ImageNet 16 is a much harder task than CFAR 10, and indeed the shallow method didn't do quite well, right? Relative compared to what it did on CFAR 10. But you will note in the times, look at the times, event to get to 20% accuracy, look at the difference in the x-axis. We things take much longer here than they do in CIFAR 10, right? Because this is a much harder task for the same search space of architectures to do. And so they have to do a lot more epochs of training. But see, this is like naturally exposed to you when you set a training threshold coming from a shallow method, as opposed to hunting for it naturally on your own, right? Because how much harder is ImageNet 16 than CIFAR 10? I can't really tell you other than like, it's harder, right, qualitatively. And this quantification can just come from your shallow method. Okay, we done some evaluation on the benchmarks. So just to FYI for people who are not familiar with this kind of ranking correlation, is we use Spearman's rank correlation to report how well the ranking of what FEAR comes up with correlates to the ground truth ranking of architectures. Like the ground truth is the, recall the ground truth ranking that you would come up with if you had fully trained it, right, to full, and then taken the test accuracy. And then it's just not enough to report this. The other thing that is also quite important is what is the common, like if we come up with a particular ranking using a ranking method, which is cheaper, what is the common ratio of overlapping architectures at, let's say, the top 50% of bins, right? So in this, like, toy hand-drawn example, these are architecture indices. So these are just architecture IDs. And let's say the ground truth architecture ranking arranged them in this particular order, whereas FEAR arranged them in this particular order. What this says is that if I cut off at the top 50%, what percentage of architectures are common between these two sets at the top 50%. And then I vary the threshold, it will give me a curve, right? It's top 10, 20, 30, 40, 50%, 60, all the way up to 100, where it will become naturally, it will degenerate to the ratio of 1. But what this will allow us to see is that qualitatively speaking, does our method not only be able to discriminate between the bag of architectures performance in the same bag, but how does it do across, like, all possible bags, and especially on the high performing ones, right? Like, you might want to say that, sure, you can do good ranking, but does your ranking put high performing ones in the high performing bins? Because that's kind of important. And we will report both. Okay. So the first detailed analysis I'll show you is on Natsbench 201. Just to recall, Natsbench 201 has around 15,625 architectures. You can think of it as like a reduced Dart search space, and it looks very much like Darts, but it has much smaller number of total architectures and choices. And yeah, and it has, like, 4 nodes, and each node can have, I believe, 5 choices, and then that's how you get to 15625. Okay, and that's okay. Oh, just as an experimental detail, you may be wondering what is the shallow pipeline we used. So back before 2012, if you are doing computer vision research, your go-to features were histogram of gradient oriented gradients, or HOG, and we used just 2 hidden fully connected layers. And we just ran this, and we didn't do any hyperparameter tuning, and it just gave these approximate numbers. The numbers were not exactly 60, 30, and 20. They were around that ballpark. So we just like rounded that and said, okay, we'll take these numbers and use it on these 3 data sets. Okay, on CIFAR 100, and then this is the first plot I'm showing you. The red dot shows you, like, FEAR. This would actually not be FEAR instead of fast-arc rank. And on this column, you see the Spearman's correlation. On this column, you see that common ratio of overlap. And just for clarity, I'm just showing the top 3 bins. And these are all cumulative bins, like the top 20% includes everything in the top 10% of ground truth. And you can see that Spearman's correlation is much higher as compared to, so the blue dots here is the Pareto frontier of all kinds of things you could do, which short reg is just shortened regular evaluation, right? Like, if I were to do n epochs of training, which is the natural organic baseline where n is small, how does that Pareto frontier look like if I were to vary both batch size and epochs? right? And this is the kind of thing it etches out. And what you would want is that, okay, fear to be above this Pareto frontier in both Spearman's correlation and common overlap. And you see that on by quite a bit on CFAR 100. Okay. Sorry, yeah, go ahead.
Sorry, Dey. What is the x-axis over here? Is that the total training time, or?
Yes, it's the average per architecture training time. Yeah, but you can think of it as total, because that just multiplies it by the total. Yeah.
Okay. Thanks.
Yeah. This plot may be a bit difficult to parse, because it has a lot, it's quite information dense. So what we did was we took this particular dot, and the nearest Pareto frontier numbers that are present below the red dot somewhere, the nearest ones, and plotted them side and just put them down in a table. And this is to give you an idea of how much the numbers differ from each other. And you can see that in each of these cumulative bins, so this side is SPA, Spearman correlation, and that this side is common ratio of overlap. You see that fear does much better than doing shortened regular evaluation and picking the nearest. And these numbers come from the picking nearest Pareto frontier on both. And obviously, one thing that you will notice is that this should degenerate to 1, the common ratio, because everything, if you take all the bins, they all commonly overlap, irrespective of their ranking. And because of this phenomenon that I just showed you before of weak architectures taking longer, by definition, fear should take longer to rank architectures, especially as you include all of the architectures, all the good and the bad ones, over the bins which are only over the high performing ones, because they tend to reach threshold very quickly. Fear will take less time. But over bins which are low performing, then think of the separate bins towards the end. Those will actually raise your average time, because they struggle to reach 60% accuracy, or for example on CFAR 100, or 30% on CFAR 10 and 30% on CFAR 100, right? So by definition, fear should take longer there. And then this makes you wonder, okay, then is fear really time efficient? Because this is going to take much longer, right? And the answer is that actually in practice, no, it's actually much more efficient, because you can cut off a large number of low performing ones very quickly. And I will show you how to do that. I don't want to just show you all the most promising chart cherry pick on ImageNet 16. Even though fear is close to right above the Pareto frontier, it's not as dominating as it was in CFAR 100. But you will see in the random search results even that just because of this phenomenon that exposes the first order dynamics of weak versus strong architectures, we can take advantage of that to cut off save time by a lot. And here you can see that, okay, most of the time the differences are okay, 0.78, 0.69. It's on 10 correlation points, and then on common overlap, it's not that much different. It's close, but not really much dominating as in CFAR 100, right? On CFAR 10, it actually does pretty well. I'm just for time, I'm not included that in the presentation. It's all in the paper. So, okay, one of the things you may be wondering about is hey, what happened to these green dots here? What are those things? And those are these very recent work has proposed these zero cost proxies, right? And where you look at, you don't even and that's why they are on zero time, because they take basically nothing, right? Okay, in practice they take a few perhaps a few seconds, but for the purposes of plotting, I just made them zero. Because it's negligible compared to the thousands and hundreds of seconds here, right? And you're hey, what about this guy? And this guy is SynFlow. And SynFlow based score, where SynFlow is a pruning at initialization technique. It's Dey, shouldn't we use this? This seems amazing, right? No time, nothing, all these blue red dots, what are you talking about? And okay, so we were when we saw these plots, we were okay, I should use SynFlow. And then Seb was like, but I don't see a particular reason why SynFlow, which is data agnostic. Okay, look, most of the other measures are not very good, but at least SynFlow seems to be very good. Why don't we use SynFlow for everything and then just close the chapter on ranking architectures? So Seb suggested actually a very nice experiment where he said, like, let's generate a synthetic data set. And so we generated this 32 cross 32 data set of random RGB images, which is basically like a drop-in for CFAR 10, but generated from a Gaussian distribution, and then just did 10-way multi-class classification, where each image was labeled via randomly initialized two-layer neural networks, and you just take the argmax, like, you know, whichever neural network had the biggest score, you assign it that label, right? So this is a clever way of like generating a synthetic data set which doesn't have the usual bias of, like, you know, natural images, right? So we just wanted to generate a wonky data set, and we didn't do this. This was not adversarially generated. This was generated one fine Saturday morning and with over a cup of coffee and Python code, and this was not generated to make any other measure look bad. And then I ran, like, you know, all the baselines on it again, and I just showing all the most of the zero cost measures here, and they all take zero time. If you just put that in your head, and look that their Spearman correlation becomes almost close to zero, right? And this is really bad. Whereas fear, which takes more time, right? We have to train it. Fear is not zero cost. It is costly compared to zero cost, but fear still comes up with a reasonable number. Show does shortened, I have not included in the pod. Show does, like, you know, shortened regular evaluation. But I want to stress this point that there is that it seems that it is not enough to, for example, SynFlow is doing really well, but SynFlow, if you read the paper, doesn't take dataset into account. It's a dataset agnostic score. And there has been a recent paper from Tugener, Smidhuber, and Stadelman, who showed that the rank of architectures, CNNs, if you, and they took a architecture space which is very similar to darts, if not exactly darts. And if you take that and you run it on different data sets from scratch and train them, the ranks are not correlated to each other. Like, you know, something that performs well on ImageNet, full ImageNet data set is usually not the top performer, or sometimes is actually a weak performer on aircraft or power line or some other data set, right? So things with, sorry, go ahead. Yeah.
I haven't heard the paper, but was it with the same training pipeline for every data set, or did they use different training pipelines for each other?
I don't exactly remember, but I believe it was the same training pipeline.
Yeah, because I guess for ImageNet you might need a different learning grade schedule, or different initial learning grade and so on.
Yeah, so it is possible that factor was there. We'll have to dig into that paper, but what struck out to me is that it was not obvious that architectures were transferred in a data agnostic manner. Like, there was no intrinsic property of an architecture that made it good or bad, like, other than maybe like very extreme cases, like if I take all skip connect, I expect it to be bad on everything, right? Like, you know, compared to parameter full operations. But yeah.
Makes sense. Yeah, I have
so
to it looks interesting.
Yeah, it is possible they also ran some hyperparameter optimization, but I think they didn't run too much, and they had some good reason for it. Okay, the other thing that we looked at into is like stability as training progresses. That if I were to do, like, you know, as I train the network over epochs, how does this zero cost scores behave? Like, one of the properties you would expect of a good ranking method is that as it gets exposed to more and more of the actual task loss and data set, it should be able to do more and better, right? Like, this is strictly more information coming in. But because many of these methods, I believe, are based on pruning at initialization, the moment some gradient information goes in, the score becomes quite uncorrelated with the actual ranking of the method, and it degrades drastically, right? Like for example, SNP and grad norm. Where is SNP and grad norm? Yeah. So they actually just they start from around 0.6, which is not bad as a correlation, so Spearman correlation, and then they degrade almost quite close to 0 by 200 epochs, right? And 200 epochs is what Natsbench 201 does, and this is over that same 1,000 architectures. And yeah, so you can see that things start off well, but as epochs, if you rerun this scoring mechanism after every epoch, yeah, this is Jacob covariance. Jacob covariance is the Mellor et al. Paper, which uses the sensitivity of gradient maps, feature maps at the data points as a scoring mechanism, and the correlation between them. And that degrades from 0.69 to minus 0.02, which is almost 0 correlation immediately, right after one epoch. So this is a phenomenon. I don't have any deep insight into why this is happening, other than the fact that these the pruning at initialization based schemes really are dependent upon the initial gradient, and the moment enough gradient passes through and updates, the gradient values decrease perhaps, and then the scoring doesn't work anymore if you try to like get rank correlation. If people have other insights, I'm happy to know.
Excuse me, Dey. So for the Jacobian covariance, then you say that it goes from 0.69 at initialization, but maybe in the graph it is at 0 or like.
Oh yeah, so this is like, my fault. What happened is that when I was plotting it, I'm plotting it from epoch 1 instead of like,
okay.
Yeah, so it already like, makes it appear that it's already starts at point. Yeah, so I should have like somehow kept, I forgot to like, plot it in the beginning as well, like, before anything has happened. But I had those numbers, so I know what those numbers are. Yeah.
So like after one epoch, it just falls to negative.
Yep. It started like, imagine there was a -1 here, and it started there, and then it immediately falls to minus 0.02. Yeah.
Oh, okay.
Yeah, and it's not super surprising because it really depends upon this gradient feature maps at initialization. And my thing is that the reason it bothers me a bit that these things fall away this way. Look, SynFlow, although and SynFlow batch norm doesn't fall too much. Like just look at that because it's looking at. If you look at the SynFlow paper, it's looking at the combinatorics of how gradient flows, and that doesn't change even over epochs of training. But the thing that bothers me about SynFlow is that it ignores the dataset, right? And as we showed with that synthetic dataset, that dataset does matter. And if you look at that paper from Schmidhuber's group, that architectures are not intrinsic performance. They have usually, and it's dependent on, it's a function, the performance is a function of both architecture and the data set and task at hand. And that's what we tend to believe as well. And yeah. Okay, how do we use fear? Like in 2 minutes, so that I can give Shital time to present archive. Let's say you have like, let's take the simplest, and this is done on purpose, algorithm you can take, which is random search. And oftentimes, if you have read NAS papers, random search is not a bad baseline. Okay, the simplest thing you can do is, if you are using fear to evaluate architectures, is with random search, is keep track of the fastest time you have any architecture has taken to reach that threshold, right? Like that stage 1. The time it takes you to compute to process stage 1, and keep updating that, right? Like if an architecture comes which is better, which takes faster time, keep track of that. And then any architecture which is much slower, and you can decide the threshold. And we found that 4 to 8 times is enough. Any architecture which is too slow than the fastest till now, you can get rid of that. Like, as soon as they start exceeding the fastest till now time during training, you can be pretty sure that they are not going to be super competitive, and get rid of that, right? And this is like, just showing that in in a picture is that if I encounter one of these architectures, my fastest time will be whatever this time is, right? And then let's say I set some tolerance that, okay, I'm going to keep 4 times or 5 times so cutoff time is 4 times the fastest till now. And any architecture here, which will, the moment it starts it takes more than this much amount of time, I will get rid of them, right? During my random search, right? I will not spend time evaluating them. I don't even need their final scores. I know that they are going to be somewhere here, and we can early reject them. So, and doing this, for example, like, if I do shortened regularization with 50 epochs, and 50 epochs is on CFAR 10 is quite doesn't take that much time per architecture. And you see that, like, with the same budget, like, the budget was 500 maximum number of architectures. Because we can do this early rejection, we can reach within standard error. Like, you look at the numbers closely. These are the standard error numbers. Each experiment was done 10 times with 10 different seeds. We can spend usually, like, 2.4 times less time to reach that same accuracy ballpark, without having to spend a lot of time evaluating all the weak architectures. And this is where the time savings comes in, is that you are taking into account the first order dynamics of architectures in how easily they climb in training or validation accuracy, gives you a good indicator. And okay, ongoing next steps is we are going to try this on Natsbench 301. Arbor, I'm still having difficulties installing. You will get some emails from me on GitHub.
Okay.
That's mostly on me. I'm probably doing something wrong. And then we are trying it out with much more sophisticated algorithms than local search as well. We are also going to release a search space over transformers, where we would have, like, obviously I can't evaluate all transformers, but we will evaluate as many as we can, and then do fear over that. Hopefully we will also release the logs, just like the Natsbench 301 authors have, which has come in very handy. Fully reproducible code is part of archive. Paper is here. And now, unless there are further questions, I will hand over to Shital.
Thanks, Deepa. There is a question in the chat, which I just saw. What do you think caused the higher variance time /time till threshold accuracy for more sophisticated data? ImageNet versus DeFi.
The higher variance. Let me see. Oh, you mean in random search, Franciscus? Because these variances are a bit higher, or do you mean in? Let's see. These, let's say, yeah, these are plus.
I think it was for the first plot you showed, since the question was also like 25 minutes ago.
I see. It is possibly about this one. Yeah. So if this was about this, like, I don't really know, other than that, like, ImageNet tends to run for longer. So various, like, cluster speeds can come into account, like, because of, like, even reaching 20%, it takes longer time. So if depends on what else is running on the machine. This is on a cluster. We don't get to isolate the box to ourselves. So that there can be a little bit of, like, if somebody runs some other job gets skewed, there may be operating system stochasticities on how thread scheduling works. So some of that stuff can come in. I was referring to the plots where you compared the highest accuracy versus time until. Oh, I see. These ones. Yeah. Okay. Perfect. So are you referring to this part of, like, it has more variance here, like, weak architectures take short time, but then so here, like, I think it's just the nature of the data set. It's also a harder task. So there's more variance in what in time here. But as before, like, note that this part is the critical part when you are doing early rejection. As long as there's no late bloomers, you are not going to falsely reject a potentially high performing architecture. But yeah, this is, I think, just artifact of the data set. Yeah, I don't have any deep insight here. Okay, in the interest of time, should we move to Shital's to archive in the last 10 minutes? Yeah. Okay, Shital, take it away.
Hi, everyone. So, okay, let me share my screen. I hope everyone is able to hear me. Yeah. So let's see. There we go. Okay. So yeah, I'll give a very quick and 30,000 feet overview of Archive. So Archive is a framework we started building at Microsoft Research at around end of 2019.
Shital, I don't see your screen.
Oh, I'm sharing my screen, but is it? It shows. Okay.
Maybe Arbor can't see either.
Okay. Okay, just a moment.
Yeah, maybe try like stop sharing and sharing.
Yeah. Actually, my Zoom has disappeared for some reason. You see my screen now?
Yes, but you are not in slide presentation mode.
Yeah. So I just want to make sure it is at least now visible. Now, is it the?
Yep, it's all good.
Okay, all right. So sorry, my Zoom icon disappeared. It was showing the green screen, and I don't know. But anyway, so I restarted the Zoom. So yeah, I will give a very quick introduction to Archive, which is the framework that we have been building for NAS research at Microsoft Research. So the motivation for Archive is very simple. So there are tremendous incoming papers for NAS, and as you can see from 2015 to 2019, it's almost sort of exponential growth here. But at the same time, the community has been struggling. So there has been papers after papers where it says, hey, a lot of these things work in the paper, but not in the practice, right? And also there has been bunch of confusion. Like, for example, people have been using all kind of trainings to improve the performance. Like, for some people will train for 1500 epochs, some people will train for 600 epochs, and there are people who will like throw in the entire bucket of things like auto augmentations, aux towers is using darts, but there are label smoothing and all this kind of things which kind of like shows the higher performance, but it's not because of NAS, it's because of all these tricks that you use in training. So there has been papers that, hey, how do we make a fair comparisons? How do we make sure that all these algorithms are on the same starting platform. So and also at the same time, all this code has been distributed in many different GitHub repositories with very different coding styles. So our goal was to try to get a lot of these algorithms under same code base, and so we can make a fair comparison, and also we can have a clear delineation among between the tricks and the NAS algorithms. So this is where Archive comes in. So Arca is available on GitHub under MIT license. So one of the basic thing, two core things in Arca is a clear isolation of tricks. So if one algorithm is using, all kind of tricks like auto augmentation, then other algorithms should be also be able to use to get on the same footing. Then another most important feature that we consider is design abstraction. So I'll walk you through like a couple of examples of what we mean by design abstractions. But I think it is very powerful because it allows you to use many algorithms like Legos, and it is very extensible, which allows us to put everything into transformer domain, which where the work is now just starting. And also, we want to be able to offer a framework to non-experts, so so people having their own data sets can easily plug in their data sets and like try out all these different algorithms. So let me quickly move on to what we mean by design abstraction. So like this is something like almost everybody might have seen this. NAS usually gets centered around what we call genotypes, right? So genotypes is nothing but sort of a network description that NAS spits out, the algorithm spits out at the end of the search. But this is very limiting. And as you can say, it is kind of like, gets very unwidely. So one of the first design abstraction was to dump this, genotypes and instead introduce the concept of model description. So model description in cell-based search, you might have model description, and each model description contains cell descriptions. Within cell description, you can contain the graph description, which is a set of nodes and set of edges, and each edge might be op description. But this is a very flexible, essentially defining the graph of a search space search space in the essentially the in case of differential search, a supergraph. So what we now can do, instead of genotype, we have model description, and now you can use a model compiler which takes in the model description and spits out PyTorch NN dot module. So now this you can train and as usual. So this becomes a very flexible, because you can configure this in many different ways according to your needs. And also, one of the basic advantage of having this model description is that you can scale it. So NAS, most of the NAS algorithms have like two phases of search and evaluation. In evaluation phase, you might want to scale up the models. So model scaler can take the model description and spits out new model description, which is scaled up version. So you can search on ECFR, and you can have a scale up description for ImageNet, for example. So these design abstractions, now you can see how it fits into the bigger picture. So usually what we have a model and we have parameters. That is for example, PyTorch land, you might have something like this. Now what we are doing in Arca is, instead we introduce a concept of architecture model. An architecture model differentiates between two types of parameters. One is the model parameters, which are our usual weights, biases, and then there is the architecture parameters, which are alphas. So instead of considering alphas only for ops, you can have alphas for everywhere, anywhere in the architecture. And so architecture model is essentially one level essentially one level upgrade of a usual PyTorch model. And so we have an object model for all of this implemented in Python with a nice interface. So they are easily usable. And so what happens with usual model is you have a trainer, and then you do train. Now, similarly in our NAS world, what we can do is we have architecture trainer, which is inherited from the trainer, and it can take architecture model as input and train it. And architecture model, because it has architecture parameters, the trainer can differentiate between these two parameters. So you can apply all different kind of techniques for training the model parameters differently and architecture parameter differently. So this is a very high level look where you can have, okay, data sets where you have a search model description, and the search algorithm spits out result model description. And then evaluation will scale up this model description, and ultimately we have the final final description, which you can compile into an n.module. So one of the important focus in Archi is not just to get the architectures that is the best performing, right? So in NAS benchmark, we always kind of like get wind up into, okay, let's get the best performing architecture, best accuracy, right? But I think what is more important in the real world is Pareto friend generation. So usually in real world, you have constraint that, hey, I want to develop my model into a server or a phone, and depending on that, I have a size limitation, very, very, very strict constraint on, maybe number of parameters, flops, latency, power consumption, and all kind of things. So you have to have this Pareto friend generation where once a constraint is specified, you want to generate the best model for that constraint. And this is a much, much more harder problem and actually more useful in the real world. So Petri dish work that Dey led, it was published, I think, in Europe's 2019. In that work, the Pareto friend generation is in front and center. And this is a concept we want to evolve in Archi and enable for many other algorithms. So I'll close with where we are going. So obviously the transformers are taking over the world. In last 1 year, we have seen amazing amount of progress in that. So the question that is obviously running in many people's mind is, how do we apply NAS effectively in transformer space? So currently we are working on that particular problem, and we have a few things available right now, but it is in working stage in the Archi GitHub, and we'll be releasing the final version as we progress. So with that, we'll thank you for coming in, and thank you for inviting us to present our work. So Archi is available at GitHub. So very simple URL. So Archi, by the way, is a word. It's a dictionary word apparently, and it's it's a kind of a play on architecture AI. But I think it is a legitimate dictionary word. So, well, thank you. And if you have any questions, please fire it in chat.